So now it's on.
Yes, sir.
Yes, sir.
Pause mode. I have to check it.
So instead, you can just upload this video on the class link, whatever you've sent.
Okay, this video is actually having a very high memory. On Zoom, it is reducing automatically. I will upload the Zoom video only. Okay, and some snapshots if required. Okay, so if suppose we say theta A is equal to theta B, just for a second. Just let me hold on. If suppose we say theta A is equal to theta B, this is no more a spring element. Okay. So if theta A equal to theta B, this is as good as a moment of inertia block. Okay. So therefore, since it is a spring, there is a possibility. I mean, there is obviously possible that these won't be equal at all. So how do we write this equation? It is Tk of t equals to k into theta A difference theta B. It's relative displacement. Just hold on. So this term inside the bracket is called as relative displacement. K into theta A difference of theta B. So I hope it is clear for everyone. So this topic requires little bit of imagination, visualization. Then things will be easy with mathematics. So again, considering a 50-degree displacement at theta B and 40-degree displacement at theta A, the relative displacement of the spring will be 10 degrees. That's what you can say. And we are not working with, we are doing numerical only to find the transfer function. Okay, we never work with actual values of k, b, j, or theta, or t of t. Okay, that is not scope of the syllabus. Only to find the transfer function is our job. So let us take one small example. So before taking example, I think I will give 1 minute of time just to revise yourself, and any clarification, any queries you can ask just for a minute. Okay, I hope there is no queries. So let us take the simplest of the simple example. We have J and B elements. We have J and B elements here. And I will represent the input T of T at this particular point. At this particular point. A Shravani, are you following? Abdul?
Yes, sir. I'm following here.
Okay. Gopal Bayam?
Yes, sir. I'm following.
Okay. Niket? Niket K. Okay. So I'm applying input at this particular node. So now I need to find the transfer function. So the task is similar. Diagram is given, input is given. Then it is asked to find the transfer function. So just take this one numerical in your notes and let us, I mean the things will be easier for the next examples. So how do you mark the output variables now? So the output variables are obviously the angular displacement for the given rotational force or torque. So if you imagine this in a practical scenario, you have one shaft and you have, you have one damper or a piston, then you have a moment of inertia block or a shaft. So when you apply the rotating force to this shaft, there will be obviously a displacement at this point. Fine. So let us call it as theta of t. So before I write, you listen to my explanation. when we apply some torque to this shaft or a moment of inertia block, obviously there will be displacement at this end. So whatever is the displacement occurring at this end, the same displacement will occur at the other end of shaft also, because it is a solid element. The moment of inertia block, you can assume or imagine it as a solid element like shaft. So if there is a 10 degree of displacement here, the other end also will have a 10 degree of displacement. And since this solid element or this J block is connected to one free end of the damper, so the other, this end of the damper will also have a 10 degree of displacement. That's obvious, fine. So there's no doubt, whatever the displacement occurs on the shaft or with respect to the shaft block or the moment of inertia block, the same angular displacement occurs at this end of the damper also. And let us look at the other end of the damper. So other end of the damper is connected to this rigid body. So it is fixed connection. It doesn't allow you to rotate at all. So that's what the meaning of this symbol. So the other fixed end of the damper will not rotate at all. So at this point you can say there is a 0 radians or 0 degrees of displacement. Fine, is it clear for everyone? So let us see how we can represent the angular displacements or output variables in this particular example. So let me mark them as theta of t and the other side of the moment of inertia as also theta of t. Theta of t, so both are equal. And this I will call it as 0 radians or 0 degrees of displacement. So this is how we can mark the output variables. Any doubts with this diagram? So I said earlier, please clarify your queries or doubts during the basic examples only. So things will be easier when we go for the complicated examples. So is it correct? I marked theta and then 0 degrees. This is correct. Monica, are you following?
Yes, sir.
Okay, then let us see how to write the differential equation for this system. Differential equation for this JB system. So one simple understanding is the torque applied is balanced by both J and B, both moment of inertia and damper block. So applied torque is balanced by both elements. So that is as good as writing T of t equal to J d square theta by dt square plus B d theta by dt. Fine? Simplest. So theta of s by T of s can be obtained by applying Laplace transform. So that will be equal to J s square plus B s. Or make a simplification by taking s as a common element. It will be s inside bracket Js plus B. So I hope everyone should follow this. This is the simplest example. So next let us take another scenario. So I would like to ask one question to you before proceeding with next example. Take this scenario. So let us connect the same blocks in the same order. And now I will change the position of force applied. T of t equals to torque position I am changing. So I am applying this torque at this point. And what is the transfer function? Can anyone answer me?
Zero.
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 We got zero.
Zero, sir.
Yes, sir.
Zero. Okay, those who said zero, can you tell why it is zero? Anyone?
Sir, as it is fixed and the torque we required will be like infinity. So once we write Laplace and we take ratio, then the denominator will be infinity, that tends to zero.
Okay. That's one way of explaining. Anybody else? So I would like to comment. Yeah, come on.
Since it's a rigid and so we can't rotate it. So
We can't rotate it. That's the simplest answer. Say one particular comment with earlier answer like infinity and all. You should make a simplest conclusion. When you try to do with the mathematics without physics, things will become complicated. So the simplest thing is whatever is your output, input applied. I repeat, whatever is the input applied, there won't be any angular displacement at all. So you are, it means you are as good as trying to rotate a pillar of a building. Okay. So when there is no output at all, obviously theta will be 0. The transfer function will be 0, whatever the shape of input given. So I hope this answer is clear for everyone, and I hope your concept is also clear parallelly. So let us take the next type of numerical. So let me consider again moment of inertia and a spring, and again this fixed block, I mean the rigid body connection with spring, and then another rigid body or a ground you can say, which is friction B caused due to the moment of inertia block. Okay, so this is the next level of numerical. So representing friction at this point means your moment of inertia block is experiencing some friction. Your shaft, I mean the shaft of the machine, a DC generator motor, is experiencing some friction, and this is spring effect. So how we can simplify this? So first job is to identify the output variables. Okay, no doubt. So how we can simplify it further? Those who can do it can proceed, and remaining just take a 30 seconds of time to think about this. We need a transfer function, and we want to identify the output variables. Just tell me how many output variables do you expect with this diagram?
1.
Anybody else? Anybody saying 2, 3? Anybody saying data is insufficient? So let us see how many output variables exist. So let us go by the concept. Don't look this diagram and decide. That's very important. Okay. Go by the concept and then try to identify. So once we solve more numericals, eventually we'll get into it very easily. So now I will redraw the same diagram in a different way. So how I can represent? So representing a damper in this way, representing a damper connected to this rigid body is as good as representing the damping effect between J and ground, or a friction effect between J and ground. Is it clear for everyone? So the friction between this moment of inertia block and the ground, I am representing as a frictional element connected to this fixed end and one free end to J. So this is another way of representing. So can we represent our output variables in this diagram? Yes, of course we can, but let me make things more simpler. Just last step, another way of writing the same diagram. Some textbook refer to this different types of diagram, is to represent the friction in this way. So all four depict the same meaning. So to mark the output variable, let us first write torque T of T. So how you can visualize is, if a moment of inertia block, okay, or a shaft element is connected to a spring and a frictional element.